Hello, this is a recorded video on the explanation of the manual for the fifth experiment in Physics 71.1. So for this experiment, you have two objectives. So first, you want to verify the conservation of energy and angular momentum for a system of disks rotating about their central axis. And second, we should be calculating quantities such as net torque, kinetic energy, angular momentum, and the work done by friction for a disk rotating about its central axis. So let's have a short introduction. So rotations play an important part in understanding the behavior of systems like rotating wheels, spinning tops, or the motion of planets around the solar system. So the concepts of conservation of energy and angular momentum are greatly beneficial to determining the quantities of motion associated with rotation. So the goal of this experiment is that you will verify these conservation laws and related quantities by analyzing motion related to rotation. So you will also be testing for the perfectly inelastic collision of a system of disks, as well as calculate many rotation-related quantities such as torque, kinetic energy, and work done by friction. So now let us discuss some of these quantities that we will be tackling. So we define the torque. So the torque is the tendency of a force to rotate an object about some axis. So if the force is a quantity that is required to induce motion, so in turn, torque is a quantity required to induce or to stop a rotation. So the formula for torque is given by this cross product here. So where R is your displacement vector from the axis or pivot point, and your force is your applied force. So the net torque experienced by an object causes an angular acceleration defined through Newton's second law for rotations. So this is an analog to your F is equal to ma for forces. So for rotations, you have tau is equal to I alpha. So your quantity I here is your moment of inertia, which we will be discussing a little bit later on. So here we have this moment of inertia. So the moment of inertia is like the rotational equivalent for the mass of your object. The moment of inertia basically measures the tendency of a object to resist any applied torque to it. So a moment of inertia will have a formula dependent on what the shape of your rotating object is. So for example, I'll go to lecture 21 of your physics 71 slides. So the moment of inertia for different shapes is given by these sets of equations. So for example, if you will be able to spin a rod through its center, so its moment of inertia will be given by this formula here. So if you had a sphere, you would also use this formula instead. But for this experiment, what we will be using is a disk. In particular, we will be using a hollow disk or a donut shape. So there will be a hole in the middle. So in particular, this disk will have a moment of inertia given as follows. So the moment of inertia of this disk is 1/2 m. So m is your mass, and r1 squared plus r2 squared. So r1 is the inner radius and r2 is the outer radius. So the net torque on the rotating disk is therefore the product of this equation, equation 3, and the angular acceleration, which we will be dealing with later on. So next, let us discuss the conservation of energy principle. So you may already be familiar with the conservation of energy principle, when applied to linear motion. However, we will be dealing now in particular with rotational motion. So the total energy, so this is for any case, is the sum of the mechanical energy and the internal energy. So the mechanical energy is defined as the sum of your kinetic and potential energy. So for a disk rotating at a constant height, the change in mechanical energy is due only to the change in the kinetic energy of the system. So this change in kinetic energy, so this expansion here, let's go back to lecture 21. So it actually comes from the expression for the rotational kinetic energy. So this one. So the energy of a rotating body is equal to K is equal to 1/2 I, your moment of inertia, times the square of your angular velocity. So this is how fast your rotation is happening. So the difference between these two energies will be given as the difference in mechanical energies as well. So here in equation 4, omega I and omega F will be your initial and final angular velocities, respectively. So next, we also have the work done by friction on the disk. So the work done by friction increases the total internal energy of our system. So by using our first equation, so the first equation here is tau is equal to R cross F. So the torque applied by friction is tangent to the inner radius and is given by tau is equal to FR1. So they are perpendicular, so the cross product disappears. Under the constant friction assumption, the work done by friction can be written as follows. So this will be W friction is equal to negative of your tau times the change in the angle, or this is what we call the angular displacement of our disk. So if we say that the energy is conserved between the initial and final states of spinning, then what should happen is that your delta E should be 0. So the total change in energy is the sum of changes in the mechanical energy and internal energy. So if there are no forces, external forces acting on your system, then we will have a conservation of energy, which is mathematically represented by this equation 6. So now let's move on to a perfectly inelastic collision. So elastic and inelastic collisions, these have already been discussed in the context of linear motion. So this will be lectures 17 to 19 of Physics 71. So for rotation, let's consider a first disk rotating about its central axis. So if we drop a second disk onto our first disk, we will have a composite two-disk system that will rotate with some angular velocity. So if we want to determine the total angular momentum, what we can do is sum over all angular momenta. So this is initial moment of inertia times its initial angular velocity. So this is for each object. So basically, for example, if I had maybe two objects, so my conservation of angular momentum would be, for example, I1 omega 1 plus I2 omega 2. And if I had more objects, I can simply write plus plus plus. So just to add on to this, so if a net torque is applied for some time interval delta t, the disks will experience a rotational impulse of the form J is equal to tau delta t. So again, this is a summation. So this means that for every applied torque, external torque on the system, this will result in some non-zero rotational impulse. And if the net torque is 0, then the rotational impulse angular momentum theorem will suggest that angular momentum is conserved. So this statement of conserving angular momentum will be applied in this experiment. So note, if you remember your linear momentum conservation, the form of the equation used was P1 plus P2 is equal to P2F plus P1F. So in this case, the conservation of angular momentum would actually be something similar. So for example, if I have, let's say, Li is equal to Lf, then if I rewrote this, I would have maybe I1 omega 1 I plus I2 omega 2 I. This would be equal to something like I1 omega 1F plus I2 omega 2F. So these would be superscripts, I mean subscripts rather. So these are some ways that you can apply the conservation of momentum formula. Okay, now let's move on to the materials used for this experiment. So this time around, you will be directly dealing with data obtained beforehand, just like you have done in experiments 2 and 3. But still, I will show you how the disks are operated, basically. So the experiment will require the following equipment. So here's the procedure. So let's look at this for a while. So the first procedure is to calculate the moment of inertia of the disks. So here, these inner radii and outer radii of each of the disks are already measured. So the masses are also already measured. So here you will have to calculate the moment of inertia for each disk using equation 3 and complete table W1. So don't forget to convert units. We will be looking at this in detail later on. So the dimensions and masses of the disks are already provided in the datasheet. This too will not be used in this version of our experiment. So next is the verification of the conservation of energy. So we will play a video, rotational spinning disk MP4, to show how this experiment would have been performed. So play this video. So your disk is mounted onto this motor. And once your initial torque has been applied, the disk will keep on rotating with some finite angular velocity, which will be recorded through the electronics included in the motor itself. So we will be skipping some of these parts. So we're not going to focus so much on how the data was applied, but rather I would like to show instead how these disks are operated. But the basic gist is the data that you will see later on in the tables is determined electronically and generated through the app attached to the spinning motor. So from the data that you will see later on, you can complete table W3 using table W2. So table W2 will contain the data you will need. And of course, you will have to calculate the change in mechanical energy based on our formulas earlier. So you will be given the quantities associated with the rotational kinetic energy, the work due to friction, and the percent error can be calculated as follows. So in table W4, you can complete the percent error by using this following formula. So instead of comparing a theoretical to experimental data set, what we will be doing is comparing a change in mechanical energy to the work done by friction. So next, let us deal with the verification of the conservation of angular momentum. So we will see a video again with a relation to this part of the experiment. So this video here will show initially we have our spinning disk identical to the first part of our experiment, but now let's add another disk. So adding another disk on top of the first disk will make a composite system as we described earlier with its own angular velocity. So this will be the verification for angular momentum conservation. So again, we'll be skipping these parts. So we will skip the recording parts and go directly to the 8th step here. So we will calculate the angular momentum, initial and final, using formulas that we have talked about earlier. And we will be discussing the percent error again. So this time, the percent error is determined through comparing the initial and final angular momentum states. So if you just have to follow this formula to get the value and complete table W5. So this is just an addendum. So it's not really relevant to doing the experiment remotely. But you can still read it for additional information should you be interested. So anyway, let's go to our data sheet. So the data sheet is composed of 5 tables. So for the first table, I have to calculate the moment of inertia for disks 1 and 3. So to calculate these, I will be given their respective masses and inner and outer radii. So I want you guys to be careful here kasi the units for the moment of inertia are in SI units. So kilogram times square meters. However, the masses and the radii are not in SI units, so please convert before then. Or do the necessary conversions to get the correct unit of moment of inertia. So for this section, I will have to require you to calculate the uncertainties for the moment of inertia. So the uncertainties here, you will have to recall previous concepts of uncertainty propagation way back in your first experiment. So you'll have to recall those concepts that you have previously learned. So next we have table W2. So table W2, these are just basically the data that you will have to use for table W3. So all of this is already filled out. So table W3 would be totally empty. So you'll have to determine these from table W2. So for example, my delta omega will be the change in the final and initial states. So WF minus WI. So the same would go for my delta T. So this would be delta T is equal to TF minus TI. So I want to call your attention here to the angular acceleration. So the angular acceleration is determined as the rate of change in the angular velocity. So basically, this is the quotient of delta omega over delta t. So that's how you relate your angular acceleration to your angular velocity. And lastly, we have our torque. So this is for disk 1. So the moment of inertia of disk 1 will be multiplied with the angular acceleration to get this torque as per one of our earlier formulas. So next we have table W4. So you have here your Ki and Kf. So you were already given the formulas to calculate the rotational kinetic energies. So that's 1/2 I omega squared. So you will also have your delta E as well as your work due to friction and your percent error. So all of these have formulas that have already been given in this manual. So for both tables W4 and W5, you will have trial 1, 2, 3, 1, 2, 3, which stem from trial 1, 2, 3, each from table W2. So of course, if you want to calculate the appropriate quantity, you get from the appropriate trial on table W2. And lastly, we have table W5, which is the conservation of angular momentum. So again, we have trial 1, 2, 3. So you'll have to determine the moment of inertia, IA and IB. So this IA would have to be the moment of inertia when you have one disk, and IB would have to be the moment of inertia IB would be the moment of inertia for the top disk that was dropped onto the bottom disk. So this is just one uh, one disk. So moment of inertia for one disk and the moment of inertia for another disk. So note that this is not the combination of the two disks, this IB here. This is just due to that disk dropped on top of the other one. So here you have your omega B, omega A. So you'll also have to consider the angular momentum before and after the second disk was dropped. So note here, when you are calculating the conservation of angular momentum, for this case, your LF and Li, you'll have to consider the involved objects in your equation. So for example, you'll have your Li to have one disk, but LF, how will you calculate your LF? So this is something to be careful then. And again, the percent error, that was already given as a formula earlier. So lastly, we have our questions. So here we have 1, 2, 3, 4, 4 questions. So first question, so a uniform disk with moment of inertia at the center of mass I1 is rotating with an initial angular speed omega 1 about a frictionless shaft through its center. So another disk of moment of inertia at the center of mass I2 is dropped from rest on top of the first disk through the same shaft. So give the angular speed of the composite two-disk system, assuming that the collision is perfectly inelastic. So here you'll have to derive a formula. And just to recall, we have a perfectly inelastic collision. So you'll have to recall what a perfectly inelastic collision means when you are dealing with conservation laws. So just as a hint here, what happens in the conservation of linear momentum for a perfectly inelastic collision, it's basically the same as what happens for the conservation of angular momentum. So number 2 is the total energy of the rotating disk conserved. So you can justify this using data in table W4. So number 3, in the collision of disks, the system is not isolated because of friction. How is it possible that conservation of angular momentum is still valid? So this will be a explanation. So maybe not more than 2 sentences to explain this one. And number 4, in most cases, disk 3 will not be concentric with the other disks after being dropped. So will the final speed of this configuration be greater or less than the speed in the theoretical scenario? So this one also uses the conservation of angular momentum, but also you will have to solve using the parallel axis theorem if the disk 3 is not concentric. So just as a slight tip, so the parallel axis theorem can be found in lecture 21, energy and rotation. So if we scroll down a bit, so this would be the parallel axis theorem. So this just describes the rotation of a object far from its central axis. So for example, if this tube was rotating outside of its central axis, the new moment of inertia would be calculated as follows. So this is your original center of mass moment of inertia plus m, the mass of your object, times the square of d. So this is the distance between the center of mass of your object and the new rotation axis. So that is the last question for experiment 5. So good luck and thank you for watching.